this title, okay? I modified the presentation a number of times before I could conclude on this particular one. So it's not just partial differentiation here. Okay, just go through matrices, and we have been talking matrices all along, actually. We have been talking matrices, okay? All right, so I'll just go through these first two quickly. I will just run through them without wasting much time. And then I'll focus on this last one, the partial differentiation.
Once again, the theme for today's session is linear algebra and multivariate calculus with Python for AI applications. And as the facilitator has been taking us through the lecture, he's been taking us through, the mathematics and how it applies to AI applications. And in this next session, we'll be going through matrices and matrix decomposition, gradients and partial derivatives, and chain rule. So let's also pay attention like we've been doing, and people have just been generally attentive and following through. So thank you.
Dr. Shi, thank you. I'm back.
All right. Thank you, sir.
Okay. All right. Let's, like I said, I'm interested in this final part because we have been discussing matrices all along, vectors, matrices, okay? So let's just go through this first two quickly, and then we'll move to partial differentiation, and then we close. Okay. I've presented background before on matrices, okay? Here, just showing some properties and then operations of matrices, okay? The first one here is the determinant of a matrix, okay? The determinant of a matrix. This is actually the determinant of a matrix. I know you are familiar with how to just calculate briefly, run through the determinant, but this is what the determinant is actually doing inherently, okay? Yeah, the determinant of this scale matrix is the factor by which the transformation, this linear transformation changes volumes in an n-dimensional space, okay? X is a number of points in that space now. When I say xi right now, it means we are having several vectors, okay? If in the space, in the n-dimensional space, okay, we have a vector, and then that vector, and then that point changes to another point, and changes until you have an enclosure, okay? Then if you take this matrix and then apply it on those points to transform the enclosure, all right, it is the determinant of the matrix that is actually influencing, okay, that it has a great influence, okay, in that case, all right? So we say, for instance, if those points, okay, lead to an enclosure with area P, all right, then the transformation caused by this, okay, is going to have an area like this. It's just this P here multiplied by determinant of A. Okay. This is quite deep. This is very, very interesting. This is what the determinant actually does. You see, you multiply and keep multiplying, but this is what it's actually doing. When you are doing linear transformation and moving things around, moving things around is the determinant that is actually playing a very big role there, okay? So you discover all of these things, they all connect. All of these concepts, they all connect. And that is why the knowledge of linear algebra is very interesting and then sweet, very interesting and sweet, I tell you. So the first property here is the determinant of a matrix, which we all know how to calculate, okay? So I'm just going to give you the algorithm for doing that recursively. And of course, we know how to do that. So if A is an n by n matrix, A is an n by n matrix. The determinant is this, okay? That is A11 multiplied by C11 plus A12 multiplied by C12 up to plus A1n multiplied by C1n. You can calculate it along this. 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 And that is what we have here. Okay, again, thanks to the experts who develop and build some of these software packages for us. One time you just give this to MATLAB or Python or the Scilab or the application, and then you have the value. You have the value of the determinant immediately. Okay, but that is what is being done. Calculation that is being done. So the determinant is this. So this Cij here, this Cij here, we call them the cofactors of A, and this is the way to find them. I believe we all remember this, okay, in our basic matrix algebra, all right? See, minus 1 raised to power I plus j from here, then determinant of Aij, okay? This Aij is actually a submatrix that is produced after deleting certain row and then a certain column like this, okay? And then we know the determinant of a scalar is 1 by 1. Okay, these are the properties of a determinant. Okay, these are the properties. I believe you may be familiar with some of these. Okay, determinant of a identity matrix is the 1. If you have the determinant of a product of 3 matrices, okay, the result is equivalent to the product of the determinant of individual matrices like this. Okay. The determinant of an inverse of a matrix is the same thing as the reciprocal of the determinant, right? If you also multiply a matrix by a scalar and find the determinant, this is what you are going to have, okay? And then, of course, we know the determinant of a matrix is the same thing as the determinant of its transpose, okay? In linear algebra, it's also good to bear all of these things in mind, okay? Right? So that you can understand algorithms developed by others, and then you can perhaps also create your own. These are further features. If you have a diagonal matrix or triangular matrix, the determinant is actually the product of the diagonal elements, okay, which is what you have here. You can see this is representing product, okay, from I to 1 to n, and you see I, meaning the elements along the diagonal. Okay. Similarly, we have a block diagonal or block triangular matrix. You just multiply the determinants, okay? The determinant of the diagonal block, all of them together, okay? All right. And then if you have 2 rows that are equal, of course, we say the determinant is 0. Again, this is, okay, like we have 2 rows that are linearly dependent. Let's say we have 3 rows in a matrix and 2 rows are equal. It means the 2 rows are linearly dependent. Just multiply one of them by 1, you are going to get the other. It means they are linearly dependent. It means that matrix A is not, okay, it's not fully ranked. Okay, it's not fully ranked. One row is perhaps useless there. And that is why the determinant is actually 0. The determinant will be 0 right there. Because in an attempt to move point around in that space, you move point around, all right, you find it that the enclosure you are going to have is going to be 0. The area of that enclosure is going to be 0. Okay, no change because the determinant is actually 0. All right, just because you have rows that are linearly dependent. Okay, the same also holds for coulombs. We have coulombs that are also linearly dependent. Okay, the determinant will always be 0. Okay, we also know that the determinant does not change. Okay, if the row is multiplied by a scalar and that is subtracted from another row. You know all of these elimination methods in our earlier matrix algebra classes. Okay, we remember all of this, and then we say the sign of the determinant changes if the 2 rows are interchanged. Of course, we also remember this, right? These are good to know, actually. Just keep them handy. Okay. Again, I need to point out here that a square matrix is said to be singular when the determinant is 0. Don't forget these two. And when the determinant is non-zero, it is called non-singular. Okay. Okay, adjoint or adjunct of a matrix. Okay, the adjoint is simply this: the transpose of the cofactor cofactor matrix we mentioned the other time. Okay, that is the adjoint or the adjunct. Okay, and then this relationship holds, very important. You see, the adjoint of A multiplied by A is the same thing as a determinant of A times I is the same thing as A times adjoint of A. Okay. And then the inverse of a matrix, again, is adjoint of A over determinant of A. Okay? And this holds, inverse of a matrix by A is the same thing as A times its inverse, and that is going to give you an identity matrix. And then note this again, generally, if you multiply matrices together and then find the inverse of the resulting matrix, okay, the result is like this. You find the inverse of the individual matrices and then you multiply all of them together. Okay, you need to pay attention to this, right? It's also very important. You do come across it regularly when you are reading algorithms. Okay, that are developed using linear algebra concepts. Okay, and then we also talk about pseudo inverse. This is an inverse for an n by n, a square matrix. We also normally talk about pseudo inverse if the matrix is non-square. Okay. All right. For instance, a non-square matrix A, m by n. Okay. M by n. Is it possible to have an inverse? Yes, we can have a pseudo inverse. All right. We can have a pseudo inverse, and this is the way it is computed. Okay. We call this left because this is the pseudo inverse. It's appearing here. So if you multiply this pseudo inverse by A, this is what we should get. And you know why this? You remember this? Okay. This is the inverse of A. If you multiply the two together, you get I. Okay. If you multiply A and its inverse, you get I for an n by n matrix. Okay. Can we have an equation like this for a non-square matrix? Yes, it's possible. And this is what we have. If you multiply the left pseudo inverse and A together, this is what you are going to have. You can see this is also an I, but it's n by n now, n coming from here. Okay, and this is the way to compute this. I know you also have routines you can use to calculate all of this in many of these packages. Similarly, we have right pseudo inverse. See where this inverse is appearing. You also get an identity matrix, which is m by m. And this is what, okay, this is how to calculate this. Okay, the pseudo inverse is very, very good. It's very important, especially where the matrix is non-square. We have a system of linear equations, okay, that does not lead to a square matrix. Okay, in order to find the equation to solve that simultaneous equations, we normally use this concept of pseudo inverse. Okay, we talk about the rank of a matrix. The rank of a matrix, this is also a good concept. Okay, we say the rank of a matrix is the number of linearly independent columns or rows. Okay, we say a matrix is fully ranked. This is it's well ranked. All right, there is no repetition. Okay, there is no incompleteness about the matrix. For instance, if you have a 3 by 3 matrix and then all the columns, rows are independent, then that is a fully ranked matrix. No ambiguity, no repetition about it. Okay, and that is why we normally say that the rank is number of linearly independent columns. And then, of course, we know this linear independence. It means all the columns, all the rows are actually distinct. Okay. Again, we can also define the rank to be the order of the largest non-singular square submatrix of the matrix. Okay. And this is actually the approach we used to employ in those days to find the rank of a matrix. Okay. We look at the matrix and try to find the determinant. If the determinant is non-zero, then we say the order of the matrix is n. If the determinant is 0, then we have to look for the next lower submatrix and try to find its determinant. If the determinant is non-zero, and then we say the matrix is okay, of rank n by minus 1, Okay. So we say the rank of a non-square matrix, this is actually constrained by this. Okay. Can't go outside this. The minimum of m and n. All right. And then a matrix said to be fully ranked, okay, if its rank is actually n. Okay. There are also other statements which are very important when we say matrix is rank deficient, that this matrix is not fully ranked. Okay. We see this matrix A, if it is not fully ranked, okay, all of these statements are the same. If the matrix is not fully ranked, we say A is actually singular. Okay. A is singular because the determinant is of A is 0. Okay. Similarly, the determinant of A transpose is also singular. Okay. Because the determinant of A and then the determinant of its inverse are the same. Okay. So if A is non-singular, it means its transpose is also non-singular. Then if the matrix A is also rank deficient, it means that A is not invertible. It means the inverse of A does not exist. If that is the case, we also say that the coulombs of A are linearly dependent. The rows of A are linearly dependent. Okay, so the rank of a matrix is very, very important. So if the matrix is fully ranked, if a matrix is fully ranked, it means that that matrix is non-singular, that matrix is invertible, that matrix has linearly independent coulombs and rows. Okay. All right, so we have some of these elementary matrix operations. Okay. I think a number of them Professor Adetiba showed yesterday in his presentation. They are just very straightforward. Okay. And then we can follow that. We also have these special matrices, a number of special matrices, just to mention them briefly. We have been talking about square matrices. Yes, square matrix is an n by n matrix, and then the other is n. Okay. We know that the principal diagonal, when we say principal diagonal, the main diagonal, we are talking about the diagonal that actually runs from top left corner down to the bottom right corner. Okay. All right. And then we refer to the elements along this main diagonal as diagonal elements. And then we also talk about anti-diagonal elements, which also start from the top right. And this diagonal starts from the top right hand corner. Okay, you're right. Right. The left diagonal is actually the main diagonal. And then the right diagonal is actually the anti-diagonal. Okay. We also mentioned super diagonals and then sub diagonals. All right. So the diagonals, the diagonal that is actually above the main diagonal is called the super diagonal. The one that is immediately below the main diagonal is actually called the sub diagonal. Some of these terms are used often in linear algebra, which we need to also know in case we are reading materials, okay, that use some of these terms. Okay. Here we mention null matrices. Okay, that is matrices that have all 0 elements. Okay, identity matrices, which we have also discussed before. We have diagonal matrix, okay, and then we have tri-diagonal matrix. We know a diagonal matrix already. It's a matrix that has 0 of diagonal elements, all 0. Okay, all 0. The diagonal elements are non-zero. Okay, or at least one of them is non-zero. We also have a tridiagonal. We say matrix is tridiagonal, okay? If non-zero elements only exist on the main diagonal, on the first super diagonal, or on the first sub diagonal, okay? And then we refer to this kind of matrix as a bound matrix. You can see that along the center, the matrix only has values just along the center, along the main diagonal, and then the diagonal that is immediately below the main, and the diagonal that is immediately above the main. Okay, you know, those are the places you have non-zero elements. So we say this kind of matrix tridiagonal. We also come across this term in linear algebra a lot. Then triangular matrices. Okay, I know we're also familiar with this. Say matrix is triangular, right? Can be a lower triangular matrix. It can be an upper triangular matrix. And this is just the definition. It is upper, okay, if a VI elements are actually 0, Y greater than J, okay? And it's the same thing for the lower, right? I is less than J. Okay, and I know we can easily figure out this these things, okay? Also symmetric matrices. I know we have also had this before, right? When a matrix is equal to the transpose, its transpose, we say it is a symmetric. This is also very useful, all right? We say skew symmetric matrices when the matrix equals to the negative of its transpose. Okay, it's also very useful. So it's good. I also mentioned here that any n by n matrix can actually be represented as a sum of symmetric and skew symmetric matrices, as this. Okay, this part is symmetric, this part is a skew symmetric. All right, this is also very good. Okay, there are times that we look for symmetric matrices to use. Okay, and then if it's difficult to find, then we just convert the matrix. We break the matrix down. We decompose it into a sum of symmetric and then skew symmetric matrices. Okay, and then take advantage of the symmetric part of the matrix. Right? That's also good right there. So orthogonal matrices. Okay, the inverse of a matrix, if it is equal to its transpose, we say the matrix is orthogonal. The matrix is orthogonal. This is very, very important, extremely important in robot, robot manipulation. Very important. Okay, very important, really. We say that the matrix is orthonormal if the length of the vectors are also of unit length, and similarly, if the length of the rows are of unit length. Like we said before, we say the matrix is additionally orthonormal matrix. And then we have normal matrices. Okay, if this condition is true, right, transpose A equals to AA transpose, then matrix A is normal. Okay, and these are the matrices that satisfy this condition. Okay, then we have block matrices, which are referred to as partition matrices. When you partition matrices such that its elements are now submatrices, then the matrix actually becomes a block matrix. Okay, and then you can do normal matrix operations. Okay, you can do normal matrix operations, right? Just make sure the partitioning is properly done. It's done in a way that is conformable for addition and then for multiplication. Okay. And then we have a matrix norm. Just as we have vector norm, we also have a matrix norm. Okay. And then we can also use that same command in Python to find the matrix norm. The two norm of A, okay, is calculated, okay, using this, all right? And then we also have other norms. Okay, we have one norm, and then we have an infinity norm also. These are calculated, okay, using this, which are very straightforward to grasp. And of course, we can use We can use our software package to do all of this. Don't forget the norm is the same thing, just trying to compute how big, okay, the vector is, how big a matrix is, the length, the size. Okay, matrix decomposition. Matrix decomposition. Here, we'll talk about a singular value decomposition, which is very, very key, also extremely important. Some of these applications, I mentioned them earlier on. So how is this done? This is similar to eigenvalue decomposition. But in this case now, this is applicable to a non-square, mostly a non-square, even though it's, you can also do it for square. But for a non-square matrix, we can do singular value decomposition, okay? We can do singular value decomposition. And of course, we can't do eigenvalue decomposition for a non-square matrix, right? But we normally do singular value decomposition for a non-square matrix. So if you are given a matrix A, whose size is n by n, we can again write an equation that is similar to what we wrote before. Say this A VI equals to sigma I UI. Okay, here we have two different eigenvectors here. Two different ones, VI, UI. Okay, I want us to pay attention to the dimension of VI and UI here. If A is m by n, okay, and then we have VI here, then we know that the dimension of VI, of course, will be n by 1, okay? So VI is from an n-dimensional space, while UI is from an m-dimensional space, okay? So we call them right and left singular vectors of A. Right and left singular vectors of A. This is right and this is left, just as we add the right and left eigenvectors for eigenvalue decomposition. We have right and left singular vectors A. Okay, so what is this sigma I? We call sigma I the singular values of A. This singular I, the singular values of A. You remember what we had for eigenvalue decomposition? Eigenvalues. Here we have singular values. Okay, so this UI, how is it computed? How is it computed? UI is actually the right singular vectors, like I said before, but they actually represent eigenvectors of this A times A transpose. Okay, in order to find UI, we find eigenvectors of A transpose. In order to find VI, we find eigenvectors of A transpose A. Okay, that is the way to find VI and UI here. Okay, and we already know how to calculate eigenvectors. Okay, so this is not difficult. So how do we find the singular values? Okay, how do we find the singular value? The singular value actually denotes the positive square root of the eigenvalues of this. Okay, positive square root of eigenvalues of this. You have to take note of this. Okay, that is how to calculate the singular values, and they are non-negative. They are non-negative. Okay, because we are finding positive square roots now. Whatever the eigenvalues of these are, we are actually finding their positive square root. Okay. And we can write a similar equation, okay, to eigenvalue decomposition as follows. Okay, again, if we come here and then we write a number of equations as we did before, okay, for V1, sigma 1, U1, and then for V2, sigma 2, U2. So we can combine these equations together to have, okay, to have this. If we follow our discussion on the eigenvalue decomposition, okay, it's similar here, right? So we'll have this. This is the decomposition. A equals to U times sigma multiplied by V transpose. Okay, this is actually an inverse originally, but because of the nature of V, okay, this is, in fact, V is orthogonal. Because it's orthogonal, its inverse is the same thing as its transpose, as I mentioned before, that for an orthogonal matrix, the inverse is the same as its transpose. Okay, so when you bring this, when you bring all of these equations I mentioned here, okay, and you now have a capital V equals capital U sigma, okay, you can find A from there, right? Can find A from there to give you U times this multiplied by V inverse. But because V is actually orthogonal now, okay, you know why it's orthogonal? It is because UI and VI are obtained from here. They are obtained from here. When you multiply a matrix by its inverse, what you get is actually a symmetric matrix. A symmetric matrix. And the inverse of a symmetric matrix, is unique. Okay, in the sense that the eigen vectors obtained from this will actually be orthogonal. They will be orthogonal. That is, when you stack them together, you are going to obtain an orthogonal matrix. Okay, so that is why U, V here are orthogonal matrices. Okay, and again, the order of U, sigma, and V, okay, are shown here. Okay, U is n by m, V is n by n, and sigma is n by n. And this you can deduce from. This you can always deduce from. Here. Okay. Okay. This should lead to n by m. This should lead to n by n. What is the structure of this? What is the structure of this? Okay. If m is less than n, the singular values are placed on the main diagonal of the n by n submatrix of this. Okay. Otherwise, the singular values are actually placed on the main diagonal of n by n submatrix of this. Okay. Because this matrix is n by n, it is not square. It is non-square. It is non-square actually. So if you want to place the singular values, okay, along the diagonal, you have to look for a square submatrix. A square submatrix, okay? And this square submatrix is determined, okay, depending on the value of m and n, okay? If m is less than n, then it's going to be along the main diagonal of a square m by n submatrix. If n is less than m, then it's going to be otherwise. All right, so this is what we call singular value decomposition. Singular value decomposition. Again, this is also very important, very important in signal reduction, image reconstruction. All of these are very important. That is a singular values. These singular vectors, they are very important. You want to compress images, you want to reduce the features, they are very important. Okay, sigma is always like this. Okay, you see how the singular values are arranged along the n by n or the m by m submatrix of sigma. Okay, right? The other elements are just zeros. Okay. There is also a relationship between the singular value and the pseudo inverse of A. Okay. This is the way it is done. This is the singular value decomposition. The pseudo inverse is calculated as this. Okay. The pseudo inverse of this, right, instead of using the other equation I pointed out the other time, we can also use this to do the pseudo inverse. And of course, we can also do this using our Python functions or an appropriate Python library. Okay. Okay, so we also use the singular values to describe the condition number of any matrix, the condition number of any matrix. And we say condition number is the ratio of the maximum singular value to the minimum singular value. Okay, this is very important in developing algorithms, okay, solving system of equations, okay, because if the condition number is very high, okay, the matrix, the algorithm will perform poorly, okay. That is, if when you change input values, for instance, if coefficient of a system of equations change, all right, that will affect the output, okay, greatly, if the condition number is actually very, very high, all right. A system is actually well conditioned, properly conditioned, if the condition number is close to 1, very close to 1. Okay, many of the algorithms that are developed normally have this feature. Okay, you discover the matrix is conditioned such that the condition number is close to 1. By that, you see the algorithm will actually perform well. Okay, this is also Python code you can use to decompose any matrix. Okay, do SVD of any matrix. Okay, if you can easily run. All right, the other decomposition algorithms are these. We have what we call the LU decomposition, LU decomposition. L is a lower triangular matrix, and U is an upper triangular matrix. The decomposition is like this. PA equals to LU. Okay. P is a permutation matrix. L is a lower triangular matrix, and U is an upper triangular matrix. Okay. All right. A permutation matrix is nothing but a matrix that results from an interchange of the rows of an identity matrix, or the columns of an identity matrix. Okay. All right. So we can do LU decomposition by having this. Okay. We can do Kuletsky decomposition. Okay. Also, all right. A is decomposed into a product of this matrix and this matrix. This is actually a lower triangular matrix. All right. Okay. Right. We can do this through a software package, okay, by just issuing this. Many of these algorithms have specific, okay, very specific function names or command names. Many of these packages. Okay. You see, this one is Kuletsky. The other one is LU. Okay. The next one is QR. All right. We also break A to a product of QR. Okay. Q is orthogonal. R is upper triangular. Okay. And then when you run this, okay, you're also going to do that decomposition. Okay. So that is the end of the matrix concepts. The next one is partial differentiation now. Partial differentiation.
Big well done, Doc. I think
yes, Prof.
This is an interesting one.
It's a marathon.
Yeah, you want to harvest feedback. Yeah, I can see people just absorbing everything and not getting tired. I think this is a good launch for me personally.
Yeah, it's a good one, Prof.
Yeah, let's see whether we have one or two questions before you continue, at least to see, or maybe comment. Dr. Oshin?
Yes, sir.
Do you want to
comment?
Yes.
Does you have comment?
Shobola does.
Okay, Shobola, good. Shobola.
Thank you, sir, for the presentation.
Thank you, Shobola.
For instance, in wireless communication, like channel characterization, there are times that you need to decompose the channel parameter. So they make this decomposition. So they use value decomposition most of the time because of the non-square nature of the matrix. Then sometimes the eigenvalue decomposition. Then ask now is, while I was going through a lot of journals, I realized that there were some researchers that used some modifications on the Q-Harrow decomposition, for instance.
Okay, good.
Went through that algorithm, I noticed that what they did there was actually to simplify the work for them in such a way that they manipulated the matrix such that they were able to reduce or they were able to make certain number of rows and columns to be zeros so that they can easily play around the matrix and get the channel parameter. So my question is, how do we know which kind of decomposition we are to apply for a particular application? How do we know the kind of decomposition? Maybe it's going to be Q-Harrow, eigenvalue, or singular value decomposition, and the likes, so that we will not just pick any particular decomposition that we want to use for a particular application we want to use it for. That's my question, sir.
Yes, thank you, Shobola. Yeah, that's a very good question. But you know, again, for instance, all of these decomposition algorithms actually have a specific specific applications, really. For instance, you are familiar with a system of linear equations. Okay, when we want to solve AS equals to B. Okay, Shobola, when you want to find AS equals to B, you want to find X. Okay, you can apply, all of these algorithms, all of them, you can actually apply to tweak, to reduce to do row reduction. Okay, such that the last row will only have just one element which you can easily find. Okay, so it actually depends on, for instance, eigenvalue decomposition, right? You just want to find the diagonalized form of a particular matrix, right? Perhaps it may be because you want to decouple, or you have a system of equations, okay, and these equations are actually coupled together. You have interconnected part of your system. So you want to decouple this. The only way you can do this is to diagonalize the system matrix. When you diagonalize the system matrix, you have these equations decoupled, and then you can undo each individually. Okay, it's the same thing you want to do. For instance, you look at these. Okay, you look at this A. This is QR. Right. This is orthogonal. This is orthogonal. This is upper. Okay, this is upper triangular. All right. For instance, you might want to take an advantage of this orthogonality property. Okay, remember, I mentioned the other time that, two vectors are orthogonal when, all right, when their inner product is actually 0. Okay, you may actually want to take advantage of that in that particular application. You mentioned that those authors actually reduce these elements, to many of them, to 0, so that they could be able to find a way, okay, to solve their problem seamlessly. All right, if you have this orthogonal, if you can take advantage of this orthogonality, okay, you can reduce the system to that, so that when you multiply things around, you're just going to have 0. Okay, and that will reduce the complexity of the system. So it depends on the application, and then really what you intended to do. Okay. All right, Shobola. Or if Prof has applied in, you say in wireless, I've not applied this in wireless, but I've applied this a lot in control. Okay. Prof may also want to shed any some light here if you.
Any other?
Okay, I think, yeah. And I think Dr. Oshie may also maybe make an input also.
Okay, Dr. Oshie.
You know, where in the engineering space, your signal, if it is an audio signal, for instance, is one dimensional. It's one dimensional, and if you want to maybe do transmission, I won't go to video now. If you want to do transmission over a long distance, like a wireless communication,
yes,
in most cases, you are not really sending, so reducing your of reducing the dimension of your data and see which one is reproducing what you wanted accurately. So you could explore the available options.
Good.
Sometimes you may even realize that the parameters are not sufficient, and extend what is available.
And extend. That's it.
Exactly.
That's it.
So that's like I think a way this can actually be applied, especially within the communication space. Okay.
For instance, Prof, also in in control, we do design a lot. So we have a particular system dynamics model that gives us a very seamless control design. In fact, one of the things that we use this concept to do is actually if you are for example, we have a multivariable system, multiple input, multiple output systems. So the models are actually interconnected. They are coupled, very rigidly coupled. And so when you design controllers to influence this multivariable system, you discover when you finish designing one controller and you go back to design another, you have already affected something because of the interconnection. So what we normally do is also to decouple. We just separate, break the system into distinct parts so that we could be able to handle them. All right. So we also use these decomposition approaches to do this. So Shobola, so it's actually it depends on really the application, what you're actually targeting, what is the result that you're actually targeting. Okay. All right. That will guide you with respect to which of these techniques you should use. Okay. But one thing I'm happy about is, of course, you are relating this with the papers you have read. I still know that you have papers that you still read and you still see how these things are very, very useful. Okay. So I'm happy about that. Thank you, Prof.
Okay, thank God.
So let's run through the last one.
Is smiling, he's saying thank you.
Yeah, thank you. Let's run through this last one, the partial differentiation, which is calculus now. I said in our engineered world, okay, things change all the time, of course. The only thing that is a constant is actually change. We normally say in CU, okay? So it is very, very important to be able to capture the rates, the degrees at which things change. Very, very important. In life, similarly, in our systems, okay, it's also very important that we know how things are changing with the other thing, okay, or how things are changing with respect to other things, okay. You see a number of variables changing with respect to a good lot of other variables, okay. How do you capture these changes, okay? This is where partial differentiation is extremely useful. Useful in gradient descent, useful useful in finding the rate of change, and then so many other applications. Okay, so we just want to look at this here. All right, we know that in ordinary differentiation, a function with one independent variable is normally considered. Okay, so it's nothing like a partial differentiation now. We're just looking at how a function changes with respect to a changing variable, just a changing variable. So in ordinary differentiation, this is what we have. Okay, what is the rate at which y is changing with x? This is just this, and that is why it's ordinary. Okay, it's not partial. All right, but in partial differentiation, a function changes with respect to two or more variables, and each derivative of the function with respect to any of the variables is called a partial derivative. Like this, for instance, f of x, y, and z. If x, y, and z are actually changing, it means, of course, f of x, y, z will also change with respect, okay, to all of these. Okay, so you can't just say this is ordinary differentiation with respect to s. Otherwise, you are going to get an error. If y and z are changing and you don't take cognizance of these changes, you only pay attention to the change in x, you are going to have an error. So in partial differentiation, we try to capture all of these changes. Okay, and then we have a derivative of f with respect to s, derivative of f with respect to y, and derivative of f with respect to z. Okay, so how are these combined together in order to find the overall change in y? Okay, we'll talk about this here. Okay, we'll talk about this here, and this actually plays out in a typical neural network. All right, where you're actually training the network, which means you're actually trying to find the right set of values for the weights. Now, want to find appropriate values for the weight. Okay, and then in a very complicated neural network, you know, you have a number of these weights. Okay, a number of these weights, and then the output, for instance, of a particular hidden layer neuron, all right, will have to, okay, change with respect to all of these weights. Okay, we normally use this in, you know, some of these algorithms. Okay, how does the output change with respect to all of the weights? And then if you have so many outputs in this hidden layer, so many neurons with some outputs correspondingly, okay, you want to find this with respect to changes in all of these weights. Okay, you know, that's okay, that's quite going to be a complicated thing, and this is the way it is actually done, the way the weights are actually trained using some of these existing algorithms. So we want to look at how we can find this at an elementary level, which of course we can scale up to a larger system. Let me point out here that the rules for ordinary differentiation actually remain the same for partial differentiations. But thank God, you don't have to remember any of these rules. You can always use these software packages, MATLAB, Python, and the rest to calculate all of these derivatives. Thankfully. Okay, what is the basic approach? What is the basic approach of a partial differentiation? Okay, we simply perform a normal differentiation with respect to the independent variable of interest and treat other variables as constant. Okay, when we finish doing that, we move to the next variable. We find the derivative of the independent variable with another dependent variable until we are able to find the partial derivatives of the function with respect to all of the variables. I said before, Python has a symbolic math library which we can use to do all of this. Okay, right? We just simply import it. This is a SymPy, that is symbolic Python. Okay, we import it like this or as SP. Okay, and then we can do partial differentiation, symbolic partial differentiation. Okay, very easily. Okay, all right. So we can also use this. can also use this. Professor Adetiba showed some of this yesterday from just import a particular set of functions, modus, right, and use. Okay. All right, so this is exercise 1, okay, to actually get us ready for what we do shortly now. Okay, this is to refresh our memory. If you have this number of functions, okay, we are being asked to find the partial derivative of v with respect to all of these variables here, r, w, okay, right? And then we also find the second partial derivative here. And then we are to write a Python script to verify these answers, right? So these are the analytical solutions. Again, see partial of v with respect to x. Okay, x is here, but x is not here. So we know that the partial of v with respect to x here is 0. All of this is 0. Okay, and with respect to x here is just minus 5r squared. Okay, so I hope we still remember some basic calculus. Okay, you look at this, x is here, so it becomes 3wrs squared. That is the way to do normal differentiation. There's nothing special about a partial differential. Actually, it's just that we have more than one variable now that is changing. Okay, and then you capture this change by finding the partial derivative of the function with respect to each of the independent variables. Okay, so look at these two. Change of v with respect to r. See, okay, r is here, and that is why we have this differentiation. R is here, that is why we have this. R is here, that is why we also have this. Okay, similarly, w. See, w is here, so we have the change. Here is just 30. Okay, 30 w raised to power 2r. Okay, and then we can find the second partial derivative of v with respect to x or with respect to r in order to find this. Okay, either we give us this. For instance, if we look at the partial of v with respect to s, and then we now find the second partial derivative with respect to r, we are going to get this. Or if we look at the partial derivative of v with r, and then now find the second partial derivative with respect to x, we're also going to get this. Okay, so these are the analytical solutions. Let's go to our Python platform. Okay, and try to see this exercise 1. Can you see it? You define the variables. Remember, you have to import, okay, this important modules, okay, import them, and then you define your variables. In our case now, RWX are the variables, okay, the dependent variables now, and our function is changing with respect to this independent variable. So this is the way to define them as symbolic. That is, they are symbols. Just like you are doing non-number algebra. For instance, XYZ is equals to P. What is X? That is symbolic arithmetic. That is what we also want to do here. Okay, we want to find the partial derivatives of the function with respect to all of those dependent variables. So we declare them as symbolic variables. You can see how it's done. RWX. Okay, so after this definition, we go ahead to define the function. Python is going to capture it as a symbolic function. You can see 10 times omega, as we had it in the question, raised to power 3. Okay. Prof, when I was looking at Python for this workshop, and I had to find out that this is the way to find the, exponentiation in Python. I was just trying to, or in MATLAB, MATLAB, you have to go, you have to do, I was just wondering, I said, wow, this is interesting,
So it's actually more expressive.
Yeah,
Yeah, more expressive. Wow.
Yeah, really. Okay,
Yeah.
so you do this and then you multiply it by R and then you finish this. So Python will say this, okay, as symbolic, right? So the next is to compute the partial derivatives. The first, remember, you can create your own variables as you like, okay? You just follow the naming nomenclature, okay? All right, so this are the variables I created for the partial derivative of f with respect to s, partial derivative of f with respect to r and w. You see, the f, the x, that is it. So you use diff, okay, which of course I've imported already from this SimPy library. That's what I'm using here. So this is the way it is done. F is the function, and then x is actually the dependent variable. Okay, so partial derivative with respect to x, you see. So Python is going to calculate this symbolic function for us. Okay, and then with respect to r, you can see it. Python is going to calculate it for us. You can also see with respect to w, Python is also going to calculate it for us. Okay, then the second one, which is second partial derivative, you can see the first with respect to x, and then with respect to r. Python is also going to calculate that for us. And then you can print this result. Okay, you see the original function here, printed, then the derivative with respect to x, you can see it here. Okay, and these answers are the same as the analytical solutions that we have there. So if you want to do partial derivative, Python is very, very good. Has a very robust symbolic library to carry this out. Okay, let's move to now. The next one is when you have small changes. Okay, when parameters or variables, independent variables are changing in small ways now, small changes. Okay, we can also find the resulting change of the function. For instance, look at this function A. It's an energy function in electrical engineering, half CV squared. In this case, C is changing, V is changing. What is the change in A? But now we are assuming that they are changing in small ways. Okay, so let's see what, let's quickly see what we have. All right. Okay, can we see if C, V are changing in small ways? So we capture them by this, okay? Small change in C, small change in V. And then small change in A is represented as this. Okay, so this is what we are going to have. If it's changing by this, we add it to this. We add this to this. We also add this to this. Okay, in order to capture the change now. All right, so we expand this, we have this. And we have this. Okay, you just expand this. I know we can follow this. And then we can arrange this now into a sum of terms. Okay, the sum of terms which contain first degree change and then second degree change and perhaps higher degrees change. Look at this term. We only have first degree change. Look at this small change here. Small change is first degree. This term contains second degree change. You can see them. The first one here is twice, raised to power 2, raised to power 2. Okay, so if this is the case, if this has changing in small ways, if these are very small, then you discover that the scale of this, all right, okay, will be very small. So we can decide to ignore them. When we do that, we are going to have this. Okay, and that is what we now have. All right, E plus this, okay, this is what we have left, this, and then this. That's what we have left here, okay? Or we can write this as this. If we take this to this side, it's going to cancel this. All right, this is the original energy function. Cancel this, so we have this left. You can see, all right? So I want you to look at the pattern here. Change in E equals to this. Okay. Okay, can you see this CV is actually a partial derivative of E with respect to V. Why this change, okay, this here is partial derivative of E with respect to C. Okay, so this is the first important partial derivative expression you have to know. If the dependent variables are changing in small ways, okay, you can also find the change, the resulting change in the dependent variable. Okay, in this case, the dependent variable is E, so we can find a small change. That is it right there. Okay, so we can extend this to to a function with so many variables like this. Okay, so you see what we have. Small change in V now is going to give us the change in F first with respect to R, then small change in R plus this. Okay, all right, we can extend this to so many independent variables. So this exercise 2, okay, you can do this by hand and you also write Python. Okay, it's saying that if V is 50 and C is 10, find the change in E due to an increase in this. This one is increase. This change in V is now is an increase, and this change in C is also an increase. Then what is the change in E? Okay, of course, we can invoke that formula, all right? We invoke this. We find this first partial of E with respect to V, partial of V with respect to C. We have them here, okay? And then we have the change in V and C given in the question, okay, as this and this, all right? So we invoke the formula and then we substitute the values and then we have the result right there. And then our Python code can also do this. I have done that here. You can see, use diff to do this partial derivative. All right. Okay, but you have values to substitute now. So again, you pay attention here. How do we substitute the values? This is what you do. We use these subs. Okay, meaning that the C, okay, dot subs of all of this. And then look at the arrangement. Okay, C is changing. Then what is the C value? Okay, V is changing. All right, we also have the V value. Okay, similarly for this, okay, we have this. All right, so the next is to calculate the change in E. All right, okay, and then we'll have the formula. This is the formula here. Then we have the change in E, and then we can also print the result. Okay, if the E is greater than 0, it means it's an increase. If it is less, okay, if it's S, then it's a decrease. Okay, that is what we have here. So the results are also similar to what we have right there. So Python has done a good job. Here. Okay. All right. The next is the rate of change. Okay, now the rate of change. Recall again the energy function. Okay. If C and V are changing in small ways, recall this equation. All right. Now, if we know the rate at which, in the other one, we are just given that, okay, C has changed by this amount, V has changed by this amount, but we didn't really know the rate at which they changed. So if we know the rate at which they are changing now, so this is another way to approach this, okay? All right, we know the rate at which it is changing. We know the rate at which V is changing, which is this. So what we do is to divide both sides of this by T, small t, which is this, okay? And this is what we have, all right? So if we take this T to be tending to 0, okay, this equation changes to this. See, dE over dt equals to this, partial of V with respect to partial of V, which we had before. Now, this we now change to dV over dt, okay? And we can see this. We had this before. It's only one that this and this that changed. So this is what we have. If you know the rate at which they are changing now, okay, this is what we have. This is the expression we have, right? Okay. The next exercise is this. If you have an object that is changing in a two-dimensional space, in a plane, okay, and we know the coordinates of the position, okay, two-dimensional plane now, which means x and y. X and y is a two-dimensional plane, x-axis, y-axis, okay? So if a particular object is changing position here, all right, and then we know expressions that represent this. For instance, here, this is the way x is changing, this is the way y is changing, okay? X is changing with respect to, okay, some θ1 and θ2, all right? Perhaps it's actually a drone that is moving in that XY axis. It's changing. The position of the drone is changing. Okay, it's just changing, and this is captured by two important degrees, theta1 and θ2. This is the x coordinate in terms of okay, θ1 and θ2. This is the y coordinate in terms of θ1 and θ2. So you can see that this equation x is in terms of θ1 and θ2. And these θ1 and θ2 are changing. Okay, so you need to pay attention to the way θ1 and θ2 are changing if you actually want to capture the change in x. Similarly, you need to do the same thing to this. Okay, but here we are given that the theta is this radian, and its changes at this rate. Look at the rate at which it's changing, 0.5 radian per second. θ2 is also this, but it's changing at this rate. Okay. All right, so we want to find the rate at which x is changing, at which y is changing. And then we're also asked to write a Python script to verify these answers. All right, we are given that L1, that is the length of the object, okay? All right, L1 and L2 are the lengths. Okay, so how do we do this? Of course, we can invoke our formula by finding the rate at which x is changing, okay, with time. Okay? The rate at which x is changing with time. Okay. All right. So this, this is very interesting. You know why? Because θ1 is actually changing with time. θ2 is also changing with time. Okay. So the way to approach this is this: partial of x with respect to θ1. Okay. And then the θ1 with respect to t, like we add in that equation, plus partial of x with respect to θ2, and then the θ2 with respect to t. That is the rate at which x is changing. If we find this partial derivative here, this is what we are going to have, times this, the θ1 over the t. Similarly, if you find partial of x with respect to θ2, this is what we are going to have. Okay, this is a basic calculus here. Just do basic calculus, we have this. All right, so if you substitute the values, this is what we are going to have. Okay, we can do the same thing for y. All right, substitute the values, this is what we are going to have. Python is also a very good companion. Okay, a very good companion here for exercise 3. This is what we have. Again, θ1, θ2 changing, so we symbolize them as this. And then we define the function x and y. See them? Look at my own, okay? You can use different variable names as you please. And then we compute the derivatives. Can you see the derivative? Okay, partial of s with respect to θ1, okay? Partial of s with respect to θ2. Partial of y with respect to θ1, partial of, y with respect to θ2. That's what we have here, all right? And then we substitute the values of θ1 and θ2, see, like we did before, okay? And then we calculate the change in x and y, okay, due to the θ1 and θ2 changing, okay, at the rate they did. So this is what we have, all right? So we now find the s dt, okay, as this, the y dt, okay, you can see them now, right? So we also print the values, print the results. This is what we have. Okay, can see the results. They are also similar to what we had in the analytical solutions. Okay, so Python is also very good, very good, very good, very good. Okay. All right. And then changes in independent. All right, so we have changes in independent variables as functions of other variables. All right, in this case now, V is changing with respect to P and Q. All right, meanwhile, P and Q are also changing with respect to other variables R and W. Okay, look at this. V is a function equals to this function of P and Q. P is changing with respect to R and W. Q is also changing with respect to R and W. So how do we capture this? Then we find partial of V with respect to R. Okay, this R. Find partial of V with respect to, okay, this W. All right, and this is what we have. First, we find F with respect to P. Okay, and now find P with respect to R. Okay, P with respect to R plus F with respect to Q, and then Q with respect to R. That is the first one. That is to find a partial of V with respect to R. R is here, R is here. And that's why we have the similarly partial of V with respect to W. Again, we find it F with respect to P, and then P with respect to W. Okay, F with respect to Q, and then Q with respect to W. Okay, this is the chain rule. This is chain rule. You know, just like the chain rule, and you have to follow this order properly. You have to follow the order properly. Okay, assuming that V is just a function of one variable now, P, not P and Q. Okay, but now P is a function of so many others. Okay, so this is what we have, right? Just reduces what we had before, just reduces to this, the V with respect to, okay, W1, and then we have this, all right? Okay, this is a hypothetical ANN, right? Okay, one neuron in the hidden layer, one in the output layer, and two neurons in the input layer. This is the way to represent, to capture the input to the hidden layer, to the hidden neuron. Okay, this is the input to the hidden neuron, all right? And then we are assuming that the activation function is sigmoid activation function. Okay, so the question says that find the partial derivative of the hidden layer output with respect to the weights. Okay, we have two weights now. So this is actually, like I said, it's hypothetical, and then it's indeed hypothetically simple. You know, but it's just a good example here. Okay, and you can look at our results. Output of the neuron with respect to weight 1, you can see. Then output of the neuron with respect to S. Okay, with respect to S. This is S. Okay, why S is changing with W1 and W2. And that is why we have this. Okay, S with respect to W1. And then we find the output with respect to W2. Okay, and then we have it with respect to S first, and then with respect to W2. Okay, you do this calculation. All right, this is what you are going to have, which is very simple. Just differentiate appropriately, you have this. And you can express this in terms of this and this respectively. Okay, and then you can do the Python coding yourself, following what we have done now. Okay, end of part 2. Thank you, and thank you so much. I'm grateful. Thank you, Professor Adetiba. Thank you, Dr. Oshi. And then I appreciate all the members of audience for the opportunity to do this. God bless you.
Thank you very, very much, Dr. Awelewa. Thank you so much. Can you hear the applause?
Yes.
All right.
Yes, I can hear. Thank you.
Thank you very much, sir. Okay.
Thank you.
Say something.
If there are comments, then so that I do a final wrap up.
Oh, okay. Okay, so do we have comments? All right, we do.
Thank you, Dr. Awelewa, for the presentation. I would like to go to the first practical example of partial derivatives. There's a line there.
Okay.
Please, sir.
Okay. Yeah, let me go there. I'm there. Can you see my,
Yes, sir. Yes, sir.
can you see? Okay.
Yes, sir. The part where, the line where you talked about defining variables, we have been taught
Okay.
the concept already in Python from our class, but I'm thinking a couple of people to understand why W, R, and X will be equal to a particular, like the symbol part, having multiple variable names for a particular value. I don't know if you verify that part.
No, wait. This is F. This is the function. Okay. All right. So this is a variable that is changing. Okay. This is another one. Okay. So what are you actually trying to say?
So what I'm trying to say is the line of code that that follows under the define the variable part where is written the R, comma, okay, line 4, the symbol parts.
Oh, okay. Sorry. Here, right? Yeah, to define the okay, good. Yeah, okay. Yeah.
Yes.
So you said what?
The question is, how would 3 variable names, R, W, X, be equal to the symbols, the value that we have for that variable?
Okay. R, comma, W, comma, X, right?
Yes, meaning that they are
equals to this, right?
Yes, sir. Yes, sir. I need clarifications on that.
No. Yeah, okay. Yeah, this is actually, some of these, Professor Adetiba was saying yesterday that in order to be able to, somebody asks a question that in case you forget some of these, modules, these functions, okay, how do you really get to know them? And Professor Adetiba was sharing something in that line that you can resort to documentation, and then you also have this IntelliSense, okay, that Prof mentioned. All right. Okay, so all of these have their unique definitions, really. Okay, they already developed, they are built in, so they have particular format you have to follow to use them. Otherwise, because it's not something you are creating, it's not your own. So you have to look at, for instance, if you want to symbolize variables, how is that done in Python? You look at the particular routine that is used for this and follow exactly how it is done. And this is exactly what I did here. Okay. In fact, this, I know you have to symbolize the variables first if you want to use symbolic programming. Okay. And I just look at what is normally in MATLAB, we use SYM, SYM. Okay. To symbolize your variables. Okay. So already I know that there is something like that too. I just look for it and I saw this and I checked the format for doing that. I quickly followed it without thinking twice. Okay. And that's exactly what I did. Okay. So you just have to follow the particular order, the particular arrangement, okay, and the particular format for each of these. If you look at, subs here, you also see the particular pattern. You look at the arrangement, you have the variable that is changing, and then you have the value you want to substitute. This is the way it is done in Python. Okay, it's different in MATLAB. All right, can you look at this again? For the same function, look at V, a changing variable. This is the value. This is the value that is changing. You are telling Python, this value is the one changing. We have already found it before. Now substitute this value, replace that variable with this value, replace this with this value, and Python will do that calculation for you. You just have to follow the arrangement. You can't do it any other way. You are going to get, Python is going to tell you that this is invalid. That is the way to tell you that you are not following the rules of Python. We have already created our software and we have rules we have followed. So you have to follow these rules if you want to use Python. Otherwise, you have to use another language. Okay. So this is what happened here. That's exactly, you have to follow this. If you want to define for like 5 or like 10, you also have to follow. Okay. All right. Or you may also decide to say this is just R equals to symbols R here, and say W equals to symbols W, and then X equals to, right? But this is the way of capturing, all of this in one line.
Sir, I just want to say, sir, So just like
Okay.
in MATLAB, for instance, there is a symbolic code
Yeah.
that you can use. Actually use that because to define
Code. Symbolic what?
you have a symbolic
Shobola, what is that? Yes.
It's just
SYM.
force that we have there. So what is trying to do there, what the function is trying to do is, if you don't use that, Python will take it as a symbol. So if you run that code without that line of code, it will ask you terms of W, R, and X, which you are not supplying. So you are trying to solve a real life equation. So that's why you use. So anytime you're trying to solve an equation that involves calculus or linear equations in MATLAB or in Python, you have to define your symbolic line of code first, such that the program will recognize it as a variable that you are trying to input into your function, like a linear equation or an equation you are trying to work on. So you need to define that first. And if you don't do that, by the time you run your program, it will be asking you for the value of that variable that this particular, for instance, in Python, I will tell you that the variable is undefined, that W is undefined.
Yes, undefined. So
by the time of code where Dr. wrote print original function F is going to ask that F is that W in F is undefined, R is undefined, and X is undefined. So it's a criteria that you need to do first when you are trying to work on functions that involve calculus or linear equations. Thank you, sir.
Yes, that's very good. You know, and that's why I said that you know, Python is going to tell you this is invalid. Okay, if you don't do the proper thing, you have to symbolize all the variables first. You have to symbolize because you want to do symbolic arithmetic now, okay, or symbolic calculus, okay, and this is how it is okay, actually done. I hope the comment by Subola has also clarified your question. Okay, who asked that question? Was it Adenuga?
No, it's Uche from
Adenuga. Okay, Uche. Okay. Did you get it now, Uche?
I also remember that the symbols was imported from the SymPy. So it's like a function from the SymPy itself that takes in an argument.
Yes. Very good. Yes.
So we have one question here, and then we'll now take the questions online. Good afternoon. My name is Idowu Bismarck. Thank you very much.
Okay.
Awelewa. Good afternoon, sir.
Doctor. Good afternoon, brother.
Good
yes, sir.
And thank you for your good presentation. Very rich and enlightening.
Thank you.
I just want to make a comment or a contribution comments to the question.
Yeah, go ahead, sir. Go ahead and contribute.
Yes.
Thank you.
Matrix decomposition. And they asked a question, a particular question relating to wireless communication. So I want to give an example. And then we are looking at...
Yeah, please go ahead.
All right, sir. We are looking at multiple inputs and multiple output antennas. Where at the transmitter, you have a lot of antennas. And then at the receiver, you also have multiple antennas. And for each transmitting antenna, all the receivers, all the antennas at the receiver are receiving that signal. Let's assume 4 antennas at the transmitter, 4 antennas at the receiver. Meaning that at the receiver, each of the will be having each of the antenna is having 4 different signals. Each signal from each of the 4 transmitting antennas. So by the time you combine all that, you are having 16 at the base station. Right. Now, if you form a of that called a covariance matrix, only the diagonal signals are the spatial multiplexing pipes that you are trying to create. All the off are interference. They are interference. And
all the off diagonal, right?
Yes, sir. They are interference.
Good.
Yes. Interference, right. And you need to find a way to eliminate them. Otherwise,
Very
Otherwise,
good.
detector at that receiver would be just unnecessarily complex. So we need an algorithm that can do matrix decomposition for us. Right now, the question Shobola asked is, which one that we use? And the way I look at it is this. If we look at Koleski, the composition technique, is
yes.
is for n by n. But if you use singular value decomposition, it's m by n. So you need to ask yourself, my system, is it an n by n system or an n by n system? N by n means even number, even number. But if you are looking at n by n, then it means that the transmitter will have more than the receiver. So that will tell you the algorithm to use in your decomposition algorithm. I hope that explains. You understand that, Shobola? Right. Thank you very much.
Yeah, thank you, Dr. Bismarck, for that very good one. Okay. Oh, thank you. Very good. All right. I also had a similar experience. You know what I did in that case in the multi-variable system, also in control. I just diagonalized. I found a very similar one to the original one. I diagonalized, and then I have the important element along the diagonal. For the off diagonal, they were all zeros. Okay. That also solved my problem that time. All right. Thank you for sharing that. Very important. Debola, did you get that?
Okay. Julius Odunuga has a question. I thought I saw one more question about convexivity or something like that. Oh, okay. Yeah. So he asked two questions actually. The first one, I'd like to ask how partial derivatives contribute to
Yeah, this is quite enlightening.
Yeah, convexity of a function. He asked, I'd like to ask how partial derivatives contribute to the understanding of the convexity of a function. And then the second one, for variables that are not continuous, that's discrete, can we still apply the concept of derivation?
Yeah, of course. All right. Don't forget, for discrete, it's just that you have values at a discrete point in time. Okay, it's just different from a continuous. You know, at any point in time, you always have a value at discrete point in time. So it's really discrete, continuous are really not just that one is continuous value. Of course, you can always find do that. It's possible. All right. So the other one, that person is still going to optimization. But the person that asks, that is the realm of optimization, really. Of course, we use, partial derivatives, actually, all right, there to actually find the point of the maximum point, optimal. We can use partial derivatives to also do that. We have expressions for doing that. Concavity, we have, I believe. Okay, so yes, like I was saying, of course, we can use partial derivative to also do this. Normally we use ordinary derivative to find the maximum point of a function, the minimum point, and then we can also relate this. We normally relate this to how concave a function is, how convex a function is. So it's also possible with a partial derivative. Okay, like I said before, Prof may also have to create a forum where we bring in. I like that person is interested in optimization very seriously. Yes, we get to discuss some of these optimization related concepts in the future. Thank you.
All right. Thank you very much, Dr. Awelewa. Can we put our hands together for him once again? Okay. Can you give the comment that you wanted to?
Thank you.
Okay. We can't clap for Dr. Awelewa enough. Professor Awelewa. Yeah,
thank you, Prof.
In this climb, you will be addressed as a prof. You are an associate professor. So, and you did not just, you didn't confess today, you actually professed.
Yes.
And
Thank you, sir.
Yeah, and like I was.
Thanks to you, my brother. Thanks to you, sir. Prof.
I was alluding to the fact that yesterday was a gentle introduction. So, and because I knew what the pace is going to be today, and I think in a way, persons were able to still flow. If the questions that were coming out, the comment that were coming out actually indicate that persons were not lost, they were not bored. Personally, I think I like the energy, there's at the beginning of this presentation, you said you are passionate about the fundamentals. And I think at the end, you have the end have justified that statement. The passion reflected. You were not sounding tired. If we allowed you, you may even continue for the next 5 hours. So
thank you, Prof.
We commend that depth of knowledge, the eloquence with which you presented. You were teaching maths as if you were teaching which course is that now? As if you were teaching engineers in society. which is really exciting. And I think at the beginning, when I mentioned that we wanted you to use Python, it was like, oh, you would have been fine with MATLAB. I'm saying this so that people will know that when they say we, there will always be a way. When I insisted on Python, I think Prof just picked Python. I don't know how long it took him, maybe within a week. And you can see what he has been able to do with Python. He wasn't using Python before this. Please correct me if I'm wrong, sir.
No, you're right, Prof. No. You made me.
Yeah.
I wanted to use MATLAB.
Yes, I just insisted that no, we don't want. Yeah, I said we don't want MATLAB, we want Python. And if somebody tells you that he has been using Python for the last 5 years, I'm sure you will not you will not doubt it. And that is to show us that as engineers, as scientists, as research students, there's nothing too difficult for you to pick up and just unravel. So we want to appreciate you so much. Questions have been coming up. Questions have been coming up in respect of the optimization, and in fact, we've not even. I think this is just scratching the surface. So I know now the students know that they have persons they can go to when they are. Nobody should be stranded among our students, masters and PhD, with the weight
yes, sir. Yes.
With this conference of experts that we have available. You were also hearing Dr. Bismarck speaking eloquently on how this concept can be applied in wireless communication. MIMO is an underlying technology for 5G, and some of you guys are working on Cloud RAN, and some of you are working on the wireless communication space. So Dr. Oshin just decided to keep being ME. But I can
maintain a low profile.
Exactly. I can assure you, if you allow that,
yeah, very well.
Coming out exactly. So you guys, you have all it takes, and I know that you will take advantage of all this. So on this note, I want to say big well done to Professor Awelewa. Big well done. Yeah, you are an erudite scholar, and we appreciate that a lot. And we'll keep demystifying mathematics. We are bringing lifematics into mathematics. We are bringing, this concept of dy dx. We want to demystify. People think dy dx does not have any practical relevance. We want to demystify it. We want scientists and engineers to speak mathematics when they are writing, publications when they are writing dissertations. And I'm sure we are going to really achieve this. So on this note, I say big thank you, the help me, thank you, all participants, thank you. It's been a very rich session. God bless us. Yeah, thank you.
Thank you, sir.
Yeah.
Let's also put our hands together for ourselves for being amazing participants for today. Today has been a success. And we are thankful to our facilitator once again. So let's be reminded to fill the pre-workshop survey. If you've not done so, please do so as soon as possible. Okay, and a post-workshop survey will be coming up tomorrow. So please, we need you to fill the pre before the post comes up tomorrow. Tomorrow is the final day for this workshop. And tomorrow we're going to be having some topics. We're going to be having two facilitators. Artificial intelligence and the brain will be going into deep learning and reinforcement learning. So we're going to be having Professor Emmanuel Adetiba and Dr. Raymond Jules Hala tomorrow. It's going to be engaging once again. It's going to be enlightening. It's going to be an amazing time once again in this workshop. So be prepared to engage maximally. Thank you very much. See you all tomorrow.